Let's do an example work and kinetic energy problem. Now you'll notice I'm actually looking at the quiz that you guys took over section 9.1, which was just work, which is force times distance. There's an easier way to do these problems now that we understand about kinetic energy. So I'm actually going to work this through twice. I'm going to do it once from the standpoint of work and once from the standpoint of work energy. I'm going to show you how much easier it is. A 900 kilogram car moving at 20 meters per second applies the brakes and comes to a stop. Will the work done be positive or negative? Well, it's going to be negative, and from the work standpoint, the car is moving this way, and the brakes are applying the force that way, so the cosine of 180 is equal to -1, so the work will be negative. Okay? Then, if the brakes exert 1,200 newtons of force, how far does the car move before stopping? We had to know this because work is force times distance. So what we say is, all right, net force equals mass times acceleration. This is my only force acting on the car, 1,200 newtons. It's stopping it, so 1,200, but it's opposite the motion, so it's negative, equals the 900 kilograms of mass times its acceleration, and I can divide both sides by 900, and I get acceleration equals negative 12 over 9, or I'm just going to leave it like that, negative 12 over 9, 4/3 meters per second per second. Okay, that doesn't tell me how far it moves, so now I'm going to have to use the equation v squared equals v naught squared plus twice the acceleration times the change in position to figure that out. So I get final velocity 0 equals initial velocity 20 squared plus twice the acceleration, which is negative 4/3, times its change in position, which is what I'm actually trying to find. So now I'm going to have negative 400, that's that, divided by 8/3, that's twice that, but it's negative, equals delta x. And if I take 400, 3, divided by 8, tells me 150. So this thing moves 150 meters. How much work is done stopping the car? Well, now I can take my 150 meters, my x, times my force, which was 1,200 newtons, times the cosine of 180, and I get 150 times 1,200 times the cosine of 180 is negative 180,000 joules. And so it took 180,000 joules of work for friction to stop this car. D says, does the work change if the brakes apply only 800 newtons of force? Show your work, be careful. So we have to do the whole process again. Net force equals mass times acceleration, because our force changed, 900, sorry, our acceleration also changes. So now the acceleration is 800 divided by 900. That is to say acceleration equals, and this is negative again, negative 8/9 of a meter per second squared, and then I can use my v squared equals v naught squared plus twice the acceleration times the change in position to figure out how far it goes. Because the force is less and the acceleration is less, it's going to go a further distance to stop. So 0 equals 20 squared plus twice negative 8/9 times delta x. So I get negative 400 divided by negative 16/9 is equal to delta x. And if I do that, that's negative 400 times 9 divided by 16. Okay, and that gets me 225 meters. So it actually has to go 75 more meters in order to stop. So now when I take 225 times my 800 newtons of force, 800, times my delta x, I get 225 times 800, or not my delta x, my cosine 180. I still end up getting negative 180,000 joules. Okay. I had to do all these problems several times, and I see that the work stays the same. It's still 180,000 joules, but that's a lot of work. Now I want to show you how to do that exact same thing from the work energy standpoint. So I'm going to go ahead and I'm going to clear all this stuff, and we're going to go with this the other way. Will the work done be positive or negative? Well, let's see. Our change in kinetic energy, net work, equals change in kinetic energy. So final kinetic energy minus initial kinetic energy. My final kinetic energy is 0. My initial kinetic energy is 1/2 20 squared, which is decidedly not 0. So this is negative because Ke decreased. Okay? Anytime something slows down, it's losing kinetic energy, the work is negative. The The brakes exert 1,200 newtons of force. How far does the car move before stopping? This problem, the way you work it wouldn't really be any different. How much work is done stopping the car? This problem is considerably different. Now I'm going to say, okay, well, work done is change in kinetic energy, delta KE. So final minus initial, 0 minus 1/2 mass, 900, times velocity, 20, squared. So 900 times 400 divided by 2, 180,000 joules. But it's negative because it's 0 minus that. Negative 180,000 joules. Okay. D, does the work change if the brakes apply only 800 newtons of force? You'll notice force is nowhere in this equation. The work done is still change in kinetic energy. It's still 1/2 900 times, or negative 1/2 900 times 20 squared. It's still negative 180,000 joules. So no, the change in kinetic energy is the same work is done. Okay? So that's the power of the work-energy theorem. We no longer have to stop, calculate distance, calculate force, do all that kind of stuff. Okay? And I want to show you one more. This is from the quiz 9.2, and in this quiz we have a 3 kilogram cart that's brought to a rest by a spring, and it's moving at 3 meters per second. And it wants us to find the average acceleration and the average force and all that stuff. Well, that's a lot of problems, but really the whole point that I'm trying to get at in this whole quiz is how much work is done to stop the cart. Well, net work is change in kinetic energy, okay, which is equal to 1/2 mv squared minus 1/2 mv naught squared. So its final velocity is 0, its initial was 3, and its mass, I believe, is also 3 kilograms. Going to go ahead and look. Yep. So 1/2 3 times 3 squared. So this is negative 1/2 3 times 9, which is 27 over 2, or negative 13.5 joules. From there, we're supposed to go ahead and determine the spring constant. Now, this is the part where you have to think about work and energy. The cart had negative work done on it, or because it was stopped by the spring. Now, if you think about what that means, the cart lost energy. The cart lost 13.5 joules of energy. It lost that energy to the spring. So actually, the spring gained energy. So the spring has 13.5 joules of energy. That is equal to 1/2 kx squared, because the energy stored in a spring is 1/2 the spring constant times the distance the spring is stretched or compressed squared. So if we go back up and look, we had a spring constant, or we're trying to find the spring constant. We know that it compressed a distance of 0.025 meters. So 13.5 equals 1/2 k times 0.025 squared. And if we do the math there, we see 13.5 times 2 to get rid of that half, and then divide it by 0.025 squared. When we do that, we get a spring constant of 43,200 newtons per meter.